This is the circuit board of the indoor unit from a Fujitsu mini-split air conditioner. I will provide you with a complete explanation of its workings. We will analyze every point of this circuit board in detail. On this board, the white terminal is for the neutral wire, and the black terminal is for the phase or live wire. If you make a mistake in connecting the wires, for instance, if the connector is wired incorrectly with a live wire on terminal 2 and neutral on terminal 1, this PCB may initially work but will likely get damaged very quickly. This is because certain components on the board are not designed to function properly with reverse polarity. For example, diodes will not work correctly under reverse polarity, and they may fail as a result. When this happens, the PCB can also get damaged. The first step in such a case is to check the fuse. Therefore, always check the electric supply first to ensure that the phase and neutral connections are correct. If the fuse is blown, replace it. Following that, you will find a ZNR, zinc oxide varistor, which is a voltage-dependent resistor used to protect electronic circuits from voltage spikes and transient surges. If there is a voltage spike, the ZNR or the fuse will blow to safeguard the board. Beyond this, there is a complete filtering section on the circuit board that we will analyze next. This PCB is relatively compact in size, so it does not use a large number of components for filtering. Instead, essential components like capacitors and line filters have been utilized. Following these, there is an inductor with a value of 0.6 amps and 10 millihenries. After the inductor, there is a 6 amp bridge rectifier. The line filter has 2 points, one for input and one for output. Its purpose is to manage and suppress any spikes present in the incoming power supply. The inductor, located before the rectifier, plays a crucial role in filtering high-frequency electromagnetic interference, EMI, from the AC mains. This ensures clean power for the rectifier and the overall circuit, providing stable operation. Next, the AC voltage passes to the AC input terminals of the rectifier. The bridge rectifier converts the AC voltage to DC. After this conversion, an electrolytic capacitor is used. This capacitor has a rating of 420 volts and 100 microfarads, and its primary role is to smooth out the pulsating DC output from the rectifier. This ensures stable and ripple-free voltage to power the critical components of the PCB. At this point, a stable 320-volt DC is available across the capacitor. This DC voltage is then directed to the chopper. This chopper is installed, but before it, there are some additional components that are used to activate it. To turn on the chopper, a switching IC is installed. This entire circuit is referred to as an smps, switched mode power supply. The number of the switching IC is top 244YN, and it has 6 legs. Before discussing the switching IC in detail, I must mention that the IC is also protected in various ways. Although the switching IC has many built-in protection features, additional components are used for its safety. These include a 100 kilo-ohm resistor, capacitors, a 470 SMD resistor, which is 47 ohms, and a diode D7, and associated components provide a path for initial startup voltage to the switching IC. The combination of C32 and R45 works as a snubber circuit, which protects the switching transistor from high voltage spikes caused by transformer leakage inductance during switching. Apart from this, I will now explain how the switching IC operates. Let's start by discussing pin number 6 of the switching IC. Pin 6 is the drain pin, and the negative side of the system is connected to this drain pin. Meanwhile, the positive side flows through the coil of the chopper. This circuit will only be completed when the negative is supplied here. Only then will the chopper begin to operate. If the negative is not supplied, the system will not turn on. To turn the switching IC on and to protect it, a safety circuit is also present to ensure that the switching IC functions properly. Pin number 1 of the switching IC is the control pin, where feedback voltages are received. Feedback voltage refers to the voltages that are sent back to the control pin when the switching IC is briefly turned on. During this time, voltages flow towards the chopper, and the chopper begins to pass 12 volts. These 12 volts can be measured on diode number 12. For a short period, as the 12 volts appear here, they are sent to the positive side of the optocoupler circuit. The positive voltage flows through resistor number 67, which has a value of 150 ohms, and completes the circuit for the optocoupler's positive side. Inside the optocoupler, there is a diode that also needs to operate. The diode will only turn on when the negative point is connected to it, and this negative signal comes from the reference IC. Let me explain how this negative side is turned on. This reference IC has 3 pins. Pin number 2 is grounded, and the negative side of the circuit is connected to it. There is also a 0-ohm resistor installed here. In this circuit, the 0-ohm resistor acts as a jumper, connecting the negative side to the rest of the circuit. Its purpose is to simplify the PCB design by providing a connection point and enabling easier debugging or future modifications. Now, pin number 3 is responsible for turning on the negative side, while pin number 1 serves as the reference point. Voltages are supplied to this pin, and here's how. When 12 volts are supplied, they pass through resistor number 48 and are reduced in value. These reduced voltages then flow to the reference point, pin number 1. As a result, the diode inside the reference IC is turned on, completing the circuit for the optocoupler. Once the optocoupler is on, it activates the emitting transistor within it, which in turn controls the control voltages. These control voltages are also connected to the negative side. When the negative side is attached to the optocoupler, the MOSFET inside the IC is turned on. The MOSFET then connects the high negative side to the chopper circuit. In this way, the entire process is completed and the IC begins to operate properly. Additionally, this IC has several other pins connected to the circuit, and I will now explain the function of these pins as well. Now let's talk about pin number 2, but before that, note that all these pins, pin 2, pin 4, and pin 5 are grounded and connected to the same point. However, each pin has a different function. Pin number 2 is designed to shut down the system if there is an undervoltage or overvoltage issue in the electricity supply. In such cases, the IC itself will turn off. Pin number 4 serves as the source pin. Additionally, when pin 5 and pin 4 are joined, they generate a frequency of 132 kHz. I have already explained the function of pin number 6 earlier. Now, the remaining pin is pin number 3, which is used to measure the current. I will show you the circuit on the other side, where resistor number 34 is installed for this purpose. This is a 12 kilo-ohm resistor, where a preset current has been configured. If the current exceeds this limit, the circuit will shut down. Similarly, if the current is lower than required, the circuit will also turn off. In this way, both current and voltage are controlled to ensure the PCB is protected from any potential damage. This explains the functionality of the switching IC. Once the IC is turned on and becomes stable, the subsequent functions of the circuit start working. Additionally, I will explain where you should expect specific voltages. On diode number 10, you should measure 7 volts. This is the output voltage at this point. These 7 volts are directed into another IC through a jumper connected to its input. This IC is a 5-volt voltage regulator, and its input receives the 7 volts. One pin of the IC is connected to the ground, and the output voltage is provided through another pin. On diode number 9, you should measure 20 volts on its cathode side. If 20 volts are present at this point, the 15-volt voltage regulator will start working. Otherwise, it will remain non-functional. In such a scenario, the regulator needs to be checked. If there are no voltages present at these points, the issue lies with the chopper circuit. However, if the required voltages are present, the problem may be with the voltage regulator itself. Additionally, if 15 volts are present but do not reach the voltage regulator, the issue likely lies with the 0-ohm resistor located at the point marked JM9. This resistor is specifically designed for this purpose. If any problem arises, this resistor will burn out, preventing the 15 volts from reaching the voltage regulator. Without these voltages, the regulator will not function. Therefore, check this point carefully, as repairing this part significantly increases the chances of fixing the circuit. Now, let me explain how the fan works and the voltages present at various points. Pin number 6, you should measure 320 volts. Pin number 5, this pin is empty. Pin number 4, it is connected to ground. Pin number 3, you should find 15 volts here. Pin number 2, this pin receives reference voltages, which should be between 5 to 8 to 9 volts, depending on the fan's speed. The last pin, this is the feedback pin that sends signals back to the microcontroller through the optocoupler. It provides feedback to indicate the motor's RPM. The reference voltages are managed by IC number 10, while IC number 14 handles the feedback and sends it back to the system. I have now provided almost all the voltage points you need to check and the expected voltage values. By checking these points, you can determine whether the problem lies with the chopper circuit or the switching IC. These steps make it much easier to diagnose the fault. After this, you should also examine the low side of the circuit. Let's start by analyzing this side first. Here, an EEPROM is installed, which coordinates with the microcontroller, processes data, and sends signals back to the microcontroller. On the EEPROM, pin number 8 is connected to the positive supply, and pin number 5 is connected to the ground, where you should measure 5 volts. If 5 volts are not present at these pins, the IC will generate an error. The microcontroller may still function, but since the data is not being processed, it won't be able to perform further operations and will display an EEPROM error. Next, there are 3 ICs installed, all of which are ULN 2003. These are used to control the swing motor. On pin number 1 of each ULN 2003, 12 volts should be present. The reference ground for these ICs is the reference voltage, which gets activated when the microcontroller turns on the reference signal. Once the reference ground is activated, the circuit is completed and the motor starts functioning. Additionally, a microcontroller is installed on the circuit. Its pin numbers 19, 20, 56, and 59 should all have 5 volts present. If 5 volts are not found at these pins, the circuit will not function properly. I hope this information has given you a comprehensive understanding of this circuit and its working principles. Click on the left or right thumbnail to watch our next videos, and subscribe. Thank you.